Please don't abandon your exams. They love you, you should love them. So please answer the question. Here you see the statistics. This is us. That's a year ago. I always give a comparison a year after year after year, and the results are very close always. So far, everything is normal. Well, we did a little bit better this year. Yeah. We have people with 40 we didn't have last year. But again, on average, everything is very, very close. So nothing really unexpected. And I think 7 people left the feedback page. It's on the Blackboard as well, and always welcome. Thank you very much. And again, they're opposite and absolutely common suggestions about teaching fellows. Some like, some don't like, even in the same section. And about the length of the labs, which not a lab, as you know, but a lab plus an additional hour of the discussion. So that's a specific feature of this particular course. And again, you can read, and feel free to post any comment on Piazza if you want to, anything, because you can do it anonymously, or you can just send an email to me. Some person actually signed the feedback. I cut it out because it's supposed to be no name. And so please, we have 2 weeks before the next exam. I believe if I try hard enough, we could change the room. I like the room, except it was too hot. Maybe this time, if they turn the air conditioning on Friday, by Monday, it will be cool enough. Yeah, it just takes a lot of time to cool down such a huge amount of air. So, and they knew we were coming, but they still wouldn't be ready. So these are slides from lecture number 1. I have to go through those again very quickly. First of all, I need to remind you that standard sources for all exam problems homework, lectures, and labs, equally important. And also, different students have different learning style, different teachers have different teaching style. That's, I think, perfectly normal. Some people don't like tomatoes. Some people don't like physics. Some people don't like people who teach physics. So it's absolutely normal, but you have to make your decision because you still have time. If you really, 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 really hate it, you have a choice. If you stay, it's your choice. You know, it's like Donald Trump and I, we can't change anymore. It's too late for us. All right, now, an experiment I'm going to show you is just a copy of an experiment we saw on Friday with a little twist. So what we have here is a power supply. A wire is connected, and here you can see green mark, green tape, and the blue one. And if I turn, now watch closely. I'm going to turn the current on. Did you see any movement? All right, that's what you have to look at, the motion of this. wire. The motion of the wire tells us how the force acting on this wire from magnetic field points, and the red pole of a magnet represents the north pole. And the direction of magnetic field, force, and electric current are related by the right-hand rule. So in this situation, what we know is the direction of magnetic field. Do we know it? How does it point? How does magnetic field point? And so I'm going to switch to the camera in a moment. Please make the selection, or at least two, so you could switch quickly if you change your mind. And again, what do you think is the direction of a force acting on this wire? How does it point? Well, for you, this is the top view. This is what I see from above. So the directions we see here is away from you, down from my point of view, away from you, or toward you. Well, technically we have 6 directions: away, up, down, left, right, but only 2 matters here: this, or the original one, this. So how does force point? How? What's the word? In or out? In. That's the force. For the force, we have to use the thumb. So the question is, how the magnetic field point? How does it point? And we only have 2 options to choose from for magnetic field: from north to south and from south to north. This is something we need to know. It doesn't require understanding. It's an agreement. It's a definition. People have agreed to call that particular direction the magnetic field. And again, if we want to apply a rule, first, what should we do? We should remember, we should memorize, we should have it in our memory. If we don't have it in our memory, we can't apply. So it's like money. If you don't have money, you can't use them. So the rule says north is called magnetic field leaves the north, outside of the magnet. North, south. How do I know? I can read, and it's red. It's an agreement. It's another type of agreement. To mark the North Pole, people use red. So magnetic field lines should leave the North Pole, enter the South Pole. So these are 2 directions for magnetic field lines and for the force. And now we just have to be very careful not breaking our hand. Magnetic field lines. And the force is supposed to be down. So how does electric current point? Well, we call it to the left. It goes like this, from plus to minus. Well, It's not actually a minus here, it's just a grounded electrode, but we still remember, all the stuff we've learned before. It's grounded, black is always grounded, so it's 0. This is higher by about 30 volts. So the current goes like this. If we flip the direction of the current, if we change the direction of the current, it will change the direction of the force. Now it points up. So please, any questions? This is an important part of the reasoning. We're going to use a similar type of reasoning more and in more time in the future. We need to know very quickly. We need to be able very quickly to relate these directions: electric current, force, magnetic field, both ways. All right, so switching back. That was a review, right? Nothing new. But now, how would we show it? Using symbols. Well, we have to draw, let's say, electric current. Electric current usually is something like this, red wire. And the force was directed away from us. We have a specific symbol for that, so we have to show it. So force was down, and the magnetic field was, let's say this way, from north to south outside of it. So now we're using right hand. Again, it's a good practice. Field, force, current, right? So in here, in this situation, current. So you should be practicing with, and I think you have a homework problem when you just have to practice with this. Now, we also saw electrons traveling through magnetic field. When magnetic field acts on electrons or any other charge, the trajectory is bent. For a positive charge, we can use the same rule because, again, electric current travels in the direction of a motion of fictional positive charges. So if positive charges are not fictional, actual, still the same force would be acting with this magnitude, but the rule is the same. So for a proton or a positively charged ion or alpha particle, to relate velocity, magnetic field, and force, we can use exactly the same right-hand rule. Let's practice. So please just practice, give an answer. What do you think? I wouldn't recommend doing what you're doing. I would recommend first copy a picture and look at your picture and work with your hand and your picture. So the index finger doesn't point in the direction of velocity, it points in the direction of that component of velocity which is perpendicular to magnetic field, which is not shown here. So that's what an additional action, an additional element for you. Right here, so velocity is a vector. We can resolve, break down, split any vector into the components. This is what people usually call V parallel because it's parallel to magnetic field. And this is what people usually call V perpendicular. If this component is 0, there could be no force acting on it. when velocity is parallel or anti-parallel to magnetic field, no matter how strong the charge is, no matter how fast it travels, there will be no force. Only when there is a component perpendicular to magnetic field, the force is acting, the magnitude of the force from, well, people call it B, magnetic, or L, Lorenz's magnitude of a charge, you see? Doesn't matter, positive or negative. When we calculate the magnitude of a force, we use magnitude of a charge, magnetic field strength, and that's thing, the component of the force perpendicular to magnetic field. If this is zero, or this, there is no force. In terms of the direction now, proton, doesn't matter, magnetic field, component of a force, component of velocity, perpendicular component of velocity. So the force should point out of the screen toward us. So in this situation, you read out. It doesn't mean you have to walk away, no. It means the direction toward you, right? Please tell me what you think now. Force is acting on an electron. So we saw it on Friday, but I want to show it again. Because here, inside those tubes, electrons travel. Electrons do travel. Bless you. So let's say it's this one. The beam is undeflected because, well, magnetic field is never zero close to the Earth because the Earth is a magnet. But magnetic field of the Earth is very weak, much weaker than any magnetic field generated by any magnet like this. But I can deflect it. Similar situation, actually. That's what's happening here. Electrons travel down, velocity points down. Those are electrons travel down. Now, how does magnetic field point? What is the direction of magnetic field? At you. Those symbols represent at you. So magnetic field here points like this, travels. Now, how can I generate such magnetic field? I can use a bar magnet or I can use coils. All I need to know is the rule. Outside of the magnet, magnetic field points away from North Pole. So magnetic field points like this and it deflects the electrons. So you saw the deflection. Let's use the right-hand rule. Velocity, magnetic field, force, but the deflection was opposite. Why? Because it's a negative charge, that's it. So when we use right-hand rule to negative charges, we have to switch the answer to the opposite, because the right-hand rule only works for positive charges. Or, what else could we do? What do you think? We could use our left hand. Well, if we have it. And we do. So, if it's a negative charge, you can use your left hand. Automatically gives the right direction, correct direction of the force, and if force starts acting to the right, so the trajectory bends in that direction. That's it. So there is no left-hand rule for electric current, because electric current, by definition, has a direction of motion of fictional positive charges. But when we use actual charges, they might be positive, they might be negative. For the positive charge, we can use the same right hand. For a negative charge, we have an option. We can use the right hand and change the direction to the opposite, or we can use the left hand. Any questions? Again, it's a matter of just practice. Now, when a charge enters a region with magnetic field, trajectory is not a straight line anymore, right? What should be the shape of the trajectory? Well, what do you like more, protons or electrons? Someone said something I didn't hear, please. What did you say?
Protons.
Protons. All right. I like more electrons. The lighter, the faster. More like us. So this is the boundary between the region with nothing acting on electron, even gravity, so it just travels straight ahead, and the region with magnetic field start acting on it, and nothing else. No gravity, no electric field, only the magnetic field. So when electron enters here, that's the snapshot instantaneous velocity. What is the direction of force acting on it? Well, we know for the electron we can use the left hand velocity, magnetic field. Force should point down. Let's check, yes. So this is the direction of the force. Again, that's a snapshot here and now, but it doesn't stop, it keeps moving. How? Well, acceleration equals force, net force divided by the mass, but there is only one force, so force, magnetic force divided by the mass, which means acceleration is not zero, which means velocity must change. How? Well, the new velocity equals old velocity plus new. Old means previous, not very old, fraction of a second before, plus acceleration times time. So what we're doing here, we're adding two vectors, the green one, which points to the right, and the red one, which points down. So this plus this. How does the resultant look like? Well, something like this. So it travels certain distance, and the new velocity points like this. But it doesn't stop, it keeps traveling. The new velocity is not zero. So we can repeat the same reasoning again and again. Now, the force, the new force, which always remains perpendicular to velocity, now the new force has a new direction, which means the new acceleration has a new direction. So in a fraction of a second, this is what we need to add, this plus this. That's going to be something like this. So it moves, it reaches the new location, and it has a new velocity. It moves, it reaches a new location, and it has a new velocity. It moves, it reaches a new location, and it has a new velocity. So the trajectory is bent. You don't see it because my hand drawing is as good as my handwriting, but it's a circle. It's a circular trajectory. So let's say we have a particle right here, right now. Let's say now it's a proton. and it travels in that direction. And at this very instant, we turn on magnetic field everywhere. So not just in a certain part of the region, but everywhere. That magnetic field immediately, like in our experiment, immediately starts bending the trajectory. How? Well, in this situation, we got to use a right hand, so velocity, magnetic field, I'm going to do it here. You use your own picture. Velocity, magnetic field, force, how does it point for you? Up the screen. Exactly opposite to the electron. If the same magnetic field and the same velocity, but a different charge, the force should have a different direction. So it will travel in a circle. Do you see a circle? What does every circle have? What does every circle have? Center and the radius. And how do we call a motion like that? Velocity, points. How do we call this motion? Circular. What do we know about circular motion? Everything. So now, by the transition property of logic, we know everything about charges traveling in a magnetic field. Everything. Well, this is the standard strategy which comes from PY 105 course, because it's about force acting on an object traveling in a circle. We only have one additional equation for the magnitude of that force. That's it. There's only one simple element, an equation for the magnitude. And the rest comes from the past. If we are good at that past, we are good at the rest. So we need to draw a free body diagram, show acceleration, write the Newton's second law, and then calculate whatever we need, maybe speed, maybe period, maybe kinetic energy. That's what we're going to do now. So let's say this is a snapshot, and by the way, please tell me, is it a positive charge or a negative charge? How do you know? So the answer is, if right hand rule works, it's a positive charge. If right hand doesn't work, that means it has to be negative charge. But you can't use this picture, because if you need to use the right hand rule, you need to see all three directions: velocity, magnetic field, and what else? Force. We can see magnetic field, we can see velocity, we don't see the force. So we have to draw an arrow which represents the force. For the circular motion, how does it point? To the center. So center, and that's how force points here and now. It changes in time. It's a snapshot. It's a photograph. So now we can use the rule, and let's try right-hand rule. Velocity, magnetic field should point at us. So yes, the right hand works, which means that's supposed to be the positive charge. And there might be a question in the future when you have a picture and you need to figure out what kind of a charge is traveling, positive or negative. That's how we do it. Now we can write what? Newton's second law. This is a free body diagram. Acceleration also points toward the center. How do we call it? What's the name? Centripetal. Don't whisper. Shout. Centripetal. Because you're confident. If you whisper, it means you're not sure. So So your brain starts thinking, am I sure? Am I right? That's not good. So mv squared over r should be equal to, well, in general, the magnitude of a force acting on this particle in this specific case, at a specific force, magnetic force, or Lorenz's force, should be equal to this, which is, in this example, just speed. So all three vectors are perpendicular here. And this is the radius. There is one simplification which could be done. V and V on the left and on the right can be canceled. So mv over r should be equal to q times b. And we can solve it for whatever we wanted to. For example, we can solve it for speed, right? The radius or else we can solve it for this ratio, has a name, charge to mass ratio. Lord Thomson has become a lord because he measured this. He was not lord before, and after he became a lord. At the time they didn't have Nobel Prizes, so, but Britain, they have tiers. So it's very good to be a physicist in Britain. So if we solve it for charge to mass ratio, what we get is speed over a radius, magnetic field. And the radius is something we can measure. Magnetic field is something we manufacture by coils. And speed is something we can manage by accelerating or decelerating particles applying electric field. So this is a very fundamental result in physics. Now, this equation, as you can count, has 5 different variables. Again, depending on the situation, we can solve it for any variable we want to. And we can analyze what might happen if we change one of these variables. For example, if we increase or decrease the strength of the magnetic field acting on a particle, assuming the speed doesn't change. Now, calculate the period. A period is time for one whole revolution. All we need to do is remember an equation for a period over, no, that's not how I remember it. This is how I remember it. Speed equals distance over time, 2 pi r over time. That's not a new equation, but we can combine this equation with the speed of the charge circulating in a magnetic field, r q b over m. So 2 pi times r over, well, r q b over m. That's where we might make a mistake because it's a fraction over a fraction, but we know what to do. So we can cancel the radius. 2 pi m goes on the top, q b. So it turns out, let's say again, we change the magnetic field acting on a particle. It's the same particle, so same mass, same charge. The magnetic field directly affects the period. More magnetic field, less period, so it travels. It makes more revolutions per second. Any questions? So this is again how we got to that equation, which relates speed and other parameters. And here is the equation for the period. Now, this is a type of equation you may think about. If we have two different particles, how would we compare something? Well, you know what, not enough space. If we have two different particles, we just have to kind of solve two problems in one. One for the first particle, second for the second particle, and then just compare literally. Here, what the question is about, same period and same magnetic field. Okay, same period, same magnetic field. So there's a particle, the particle number one, there's a particle number two. T1 and T2 are equal. T1 and B2 are equal, same magnetic field. So period 2 pi m over QB. Period is equal to 2 pi m over QB. We just need to write that subscript. And now if we need to compare some variables, the fastest way is just to divide T1 over T2 should be equal to 2 pi m1 over Q1 B1 over 2 pi m2 over Q2 B2. Now we don't have 3 fraction bars, or 2 fraction bars. Now we have 3 fraction bars, which makes it even more annoying. But we know what to do, yeah, with fractions. Bless you. If we need to divide a fraction on a fraction, we just have to multiply by the reciprocal. Now, this is supposed to be equal to 1, according to this condition. And where else we can cancel these things, magnetic field. So 1 equals m1 over q1 times q2 over m2, or this is how probably we would write it. This ratio is equal to that ratio. So in this particular situation, under these two conditions, we cannot say anything about a charge per se or about a mass. They might be different, but we know that this ratio is supposed to be the same for these two particles. That's it. That's all we can say from that information. Again, mostly algebra. So same ratio. Now, what about kinetic energy? Again, just an example. Well, if we need to calculate kinetic energy, all we have to do is this, mv squared over 2. Not mv squared over r, like some people did in the example. This is not kinetic energy. This is centripetal force. And force is not energy. And energy is not force. So, hence, all we need to do is just, again, solve this equation for the speed. Again, the radius, charge, magnetic field, mass. And now just plug it in. Kinetic energy is equal to m over 2 r squared q squared b squared m squared. We can cancel one mass. So kinetic energy, r squared q squared b squared 2 over m. wherever it is now, depending on the situation, we can analyze what might happen to kinetic energy if we make a change, or how to compare kinetic energy of two different particles. Again, we just plug it, copy and paste. Yeah. It's happening again. Well, I suggest blink as fast as it. In that case, you will see the still picture. So I'll try to make a switch to a different input, but it might not help, so fingers crossed. That's why these people came in the morning, because there's some issue. And no one really knows the reason for that issue. So I'm going to switch. You saw a circle. Yeah, that was a trajectory of a particle. The question was about work done by magnetic field on that particle. So right now you can think about work in general. Does it do any work? If it does, positive or negative? Okay. See them. Open. No. Oh. See? So this is what I want to look at. Do I have a WebAssign? No, I don't. So I'm going to start it up. So again, these are, so by now you should make your mind and choose positive, negative, zero, or not enough information. Positive, negative, zero, not enough information. Positive, negative, zero, not enough information. Positive, negative, zero, not enough information. Lecture number 10. Positive, negative, zero, not enough information. So what did you say? Yes. You see, it doesn't matter if you're right or wrong. It's a matter of confidence. You can say zero. What do you say? Zero, because that is absolutely correct answer. There's no work done. Remember, everything is perpendicular to everything. If we want to calculate work, we have to multiply by cosine of the 90 degrees. So the answer is indeed zero. Because it's exactly the same type of a calculation we've done before for the force of tension. Force is not zero, but the work was zero. And for the, no, we didn't do for the gravity, but very similar would have been for the gravity. So it's a uniform circular motion. A uniform circular motion, that means kinetic energy, speed remains constant. If I ask you, sir, is velocity constant? What do you say? Think again. Is velocity constant? Not speed, velocity. What's the difference between speed and velocity? Speed is the magnitude of velocity. Velocity is a vector, so it has a direction. And speed remains constant. But velocity changes Otherwise, the acceleration would have been 0. The acceleration is not 0, it's mv squared over r. So velocity technically changes because it has different direction at different points. Velocity always just touches tangent to trajectory. So the length of a velocity vector doesn't change, the length, magnitude, speed. But if the question about velocity changes. Delta v over delta t is the acceleration, which is not 0. Well, just more examples. Here we need to solve 3 problems in one because we have 3 particles traveling through magnetic field. This is the region with the magnetic field. Do we know the direction? No. So that's probably the first question we need to answer. What we know is, okay, we don't know. Okay, we know this is a positive particle, positive. We don't know this one. So we can pick up any charge. And now we have to use, well, if you pick this charge, you have to use the right-hand rule to figure out the direction of magnetic field. So, but again, first you have to draw the second arrow, which represents what? Well, right-hand rule connects 3 directions: velocity, field, force. If we need to make a statement about third vector, no matter what it is, we need to see 2 other vectors. So let's say this is like proton or something, a positive charge. Right here, right now, what is the direction of velocity? How do you say it in words? How does velocity point? See, I'm blind. You have to tell me in words. I cannot see it. I only can hear. Right where you make the dot. Yeah, dot. I see the dot. I don't see velocity. To the right. Now, how does force acting on this charge point? No. We cannot use right hand to answer this question. We have to use right hand to answer the next question about magnetic field. So before that, we have to make a statement about the direction of a force acting here and now. How does it point? How do we know? Because the trajectory bends, curves down. So we can see actually this is the center of that. Well, it's a quarter of a circle. But all we need to see is a part of a circle to imagine the whole circle. And a force must point toward the center. Now we see 2 vectors, velocity and force. Now, because the charge is positive, we can start applying right-hand rule. We can do it now. We couldn't do it before. So what does the rule say? What is the direction of magnetic field? It's always perpendicular. The question is, how does it point? What do you think? What do you think? Velocity, force, absolutely right, out of the screen. But it points everywhere. Here, 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 and here, 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 and here, 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 and here, 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 and here. Everywhere. Velocity, force. B is out. Well, now the general strategy for solving a problem like that is always the same. Draw a free body diagram like we did and ask a question, what can I do? Now, this is not a new question. We've been asking the same question for 8 weeks now. Every time when we solve a problem, when we make a step, finish that step, we ask the same question, what can we do now? Well, we can draw a picture, then we can write the Newton's second law, then we can use the expression for the magnitude of the Lorenz's force, then we can solve it algebraically, and then finally we can calculate anything we want to. In this situation, let's okay, quickly practice. So that's magnetic field B out of the screen, and we have no numbers given to us, so that means we had to do algebra. So let's say this single square has length equal to 1a or L or G, wherever you want it. So we have three particles, A, B, C. So, okay, particle A, particle B, particle C. I just want to do everything at once. It's faster. What variables, parameters are important? Not parameters we know, because actually we don't know much. Important: magnetic field, mass, charge, radius, speed, period, kinetic energy. So first, let's write down everything we know. Magnetic field acting on all particles is the same. Now, particle A at the top has charge 4 times than particle. Actually, we don't know. Okay, so this is 4 times m, B 4 times m. This is we don't know, question mark. It means that we're treating all masses in terms of that variable m. So technically, this is some kind of a constant. I don't know, x times m. Probably we can find it. Charge A, 2 times q. C is just a q. That's an unknown. So maybe y times q. Y is some kind of a coefficient. Maybe a half, maybe 1, maybe -3. Radius. That's we can see. Particle A, so that's the center of that trajectory. So how would you write the radius for the particle A? A, just 1 times A. This is the radius, and that's what we call A. Particle B, same, right? Particle C, 2 A's, yeah, that's the radius. Okay, now we gotta start writing equations. Well, first of all, mv squared over r equals qvb for any particle. So mv equals r qb. That's how I like it, because no fraction bars. And let's see. I don't know. We can write it 3 times. A, B, 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 C, 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 C. Or in terms of our variables, 4m, that's a label for the mass of A, times VA should be equal to the radius A, charge through Q, magnetic field B. For the particle B, 4m, speed B should be equal to, what's the radius? A, charge unknown, some coefficient times Q, magnetic field B. For the particle C, unknown mass, so some coefficient times mass, speed C. So a Q has a long, and A has a short line. 2A, charge equals Q. So Q represents some positive value times B. Well, what can we do now? I can calculate different ratios. Actually, there's one more, actually force. Velocities, periods. Now, first I want to say something about this charge, QB, positive or negative. Can I use my right hand? That's my instantaneous velocity for the particle B. That's my instantaneous force for this particle. And if I try to use right hand, velocity, force, magnetic field supposed to be into the screen, which is opposite to what we have. So let's try to use left hand works. So that's supposed to be negative particle. Less than 0. Actually, that's supposed to be a Y. Right. Okay, I'm just checking everything. I have A, B. C supposed to be at least one more connection, which should, speeds. I didn't fill it up. V, that column, if we look at V's, particle A has a given speed, particle B has a given speed, and particle C has speed 4 times of that. So that makes our equations more informative. So 4mv should be equal to A2QB. 4mv should be equal to A times YQB, and X times M times 4 times V should be equal to 2 times A times Q times B. Now let's say we calculate the ratio here between A and B. 4mv over 4mv, A times 2 times Q times B, A times Y times Q times B. Everything getting cancelled, Y is equal to 2. That's the magnitude of it. The charge should be negative. So in terms of our variables, that's how we should write magnitude, 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 magnitude. So now we can try this ratio. It's not the only way to do it. I like ratios because when I do a ratio, I can cancel a lot of things. But it could be done differently. It could be have solved from this and then plugged into another. Mathematically, it would be absolutely same thing to do. So 4mv over x m 4v should be equal to a 2qb divided by 2a qb. Again, b and b, q and q, and a 2 and 2, v and v, m and n 4 over 4. So x equals 1. Turns out that the mass of this particle should be just equal to m. And of course, if we had values, if we had numbers, we could calculate all those numbers. So now, of course, we can move to the next column. For example, get all the periods, right? Okay. This equation we can write 3 times for A, for B, for A, for B, B, for C, C. So TA should be equal to 2 times pi times what is the radius for A? And VA was just V. TB 2 times pi times A over, again, I think V. Yeah, only C is different, V. So these two particles have the same period, TC, 2 times pi times the radius twice A, and speed was 4. So that's going to be 1/2 2 pi A over V. So it's going to be 1/2 of TA or 1/2 of TB, which means if a period is shorter, it means it takes less time to make one revolution. So when particle A makes 1 revolution, particle C makes 2. That's what it means. And of course, you can just plug in equation for kinetic energy or wherever you want to 3 times and see how they related. So nothing really interesting anymore. And these are answers. Question. This is a situation very important in physics and in practice. It's called a velocity selector. In this experiment, we have 2 fields acting on the same particle. What you see here is an electric field inside a capacitor. A velocity selector is a capacitor which also has magnetic field. The question is about magnetic field. So this is a positive plate of a capacitor. This is a negative plate of the capacitor. Electric field points from plus to minus. An electric field acting on a charge, a positive charge, exerts a force. But we also apply magnetic field. And magnetic field is applied in such a way so particle just travels straight through without any bending. The trajectory is just straight line, neglecting gravity. So the question is, what's supposed to be the direction of that magnetic field? How should we, well, of course, in the magnitude, but at this point is the direction. How should we direct magnetic field in order to make this particle travel through without being deflected. If we didn't have magnetic field, electric field only would generate force down, and the particle would travel like this, like a ball attracted by the Earth. But in order to prevent that from happening, we generate magnetic field. Magnetic field is related to velocity and force. And your first step should be adding those two arrows to this picture. Well, the vector for velocity clearly is just a horizontal vector directed to the right. That's how it moves. What's supposed to be the direction of magnetic field, magnetic force first, magnetic force acting on this particle? How should it point? Up. Why? To cancel electric force. So that's supposed to be the direction of magnetic force. And now we can apply the right-hand rule. Velocity, magnetic force. What is supposed to be the direction of magnetic field? Into the screen. Why should I use the right hand, not the left? It's positive. Now, how strong should be that field? That's magnetic field. Into the screen. Well, we just said that magnetic force must cancel out electric force. That means they must be opposite, and that means they must have the same magnitude. So for a charge in magnetic field, magnetic force has this magnitude. Everything is perpendicular here. For the charge in electric field, we have to remember that, even if the exam is behind, still we have to remember that. It should be equal to charge times electric field strength. Turns out this is how these variables are supposed to be related. If we generate certain electric and magnetic field in that region, particles with this speed travel through undeflected. What's going to happen if they travel faster or slower? Well, in that case, one force will be stronger than another one, and particle will be deflected. If magnetic field is stronger than needed, this force will be stronger, particle deflects upward. If electric field is stronger, particle deflects downward. And that's how we can manipulate, direct particles in the direction we want to. Any questions? Yes?
Yeah, so if that's a positive charge and the electric field's pointing down, why would the force go down?
Because of the relationship between the actual charge, actual electric field, and actual electric force. For the positive charge, electric field and electric force acting on it from the field point in the same direction. For the negative charge, they must point opposite direction. By the way, if a negative charge would be traveling, you see charge cancels. If it had the right speed, it still would get through without being deflected. All right, so we said what would be happening. They would have been deflected. We could manipulate, but also, that's not a question for you. Also, this whole theory has been and is being used right now to study properties of subatomic particles, because we can manipulate with magnetic field and electric field acting on those particles. We can physically measure the radius, and we can calculate the charge to mass ratio. We can calculate the charge individually using electric field, and in the end we can calculate the mass. And many people working here at physics department, they doing this right now in Switzerland. Why in Switzerland? Big Hadron Collider is there underground, so they don't see any sun. But this is an actual picture. Professor Ralph brought actual trajectories of particles in magnetic field. Well, I have one more thing to mention. What's going to happen if a particle is not perpendicular to magnetic field but enters at a certain angle? In that situation, velocity has two components. One component is parallel to magnetic field. Second is perpendicular. Due to perpendicular component, it spins. Due to parallel component, it travels. So it actually makes a spiral motion. And that's what's happening when cosmic particles enter magnetic field of the Earth. They start spiraling. And when it spirals very quickly, it emits photons, emits lights. North Pole lights, South Pole lights. Now, we saw this picture before. We know that to generate magnetic field, we have options. We can use bar magnet, which basically, if we look inside, has many tiny magnets, which basically, if we look inside, is many electrons spinning around and generating a magnetic field similar to this one. Or we can have a loop, yeah, or many loops connected to a battery, and electric current generates magnetic field. And the rule which relates the direction of magnetic current and the direction of magnetic field is generated, has the same name, right-hand rule. It's a different rule. It's named the same. The rule is different. So that's the rule. If we have a straight line, straight wire with electric current traveling through it, we have to grab the wire with our palm to make the wire be in the palm, between the fingers, inside it. And we have to point the thumb in the direction of electric current, in this situation up. But if the current down, so down. And then we have to look at the fingers. And the fingers show the direction of magnetic field lines about this wire. That's a rule to memorize. How do we measure it? We take a magnetic needle, a compass, and just walk around and see how it points. We know that magnetic field vector inside a magnetic needle, inside the magnet, points from south to north. So we just look, magnetic field vector number 1, number 2, connect them together, we get a line, and that's the rule. This picture shows a situation when sometimes we have to use three-dimensional representation. So this wire is horizontal, electric current travels to the right. So what do? This electric field lines go all around it, everywhere. So right here, electric field points away from you, then it goes behind. Right here, magnetic field points toward you. But if you were walking in a circle around right here, at this distance, magnetic field would be pointing down. So it's always a combination of right-hand rule for magnetic field lines and magnetic field vector, which is supposed to be tangent to the line. Question. This is an electric current, a wire with electric current. Magnetic field lines are circular everywhere about this wire. The question is, what do you think about the direction of magnetic field vector here at this point? So there is no technically good representation of a three-dimensional picture using two-dimensional space, two-dimensional surface. So you really have to use your imagination. What I usually do, and I recommend practice, I imagine that I look at it from above in quotes. I look at it, that electric current wants to kill me. That makes me sharp. So if electric current points at me, I can clearly see how magnetic field lines point about it. That's it. But to do that, I need to be able to imagine that picture. So if I imagine that picture, I can see magnetic field lines like this, which means here it will be directed into the screen. And into the screen means like this, away from us. Here, the same magnetic field would have a vector directed out of the screen or into the page. All right, let's scratch this question off. Let's just go through this. So no question. Electric current points at you out of the screen. So this is the direction of electric current, and we grab it, and the electric field lines should be circular. And this direction also has a name. How do we call it? Counterclockwise. So if you're asked what is the direction of electric field lines, you should say counterclockwise. But that is the direction of electric field lines. So electric field lines lies usually so right here, right now, what's supposed to be the direction of electric field? I say electric, magnetic field. Magnetic field. I don't know what. Yeah. I know what. Magnetic field lines always tangent or tangential, people say differently, to magnetic field vector, and magnetic field vector B always tangent or tangential to magnetic field line, and points, of course, in the direction provided by magnetic field line here and now. So this vector B represents, I think it looks like this one, represents the direction of magnetic field vector at the location of this particular point P. All right. Now, of course, we need to know how to calculate the magnitude And if we have a straight wire, the magnitude decreases with distance. This is the equation, has no name. The magnitude of magnetic field strength of a straight wire, that's the name. Yeah. Stronger current generates stronger magnetic field. Weaker current generates weaker magnetic field. And if we move away from a wire, magnetic field decreases. If we move closer to a wire, magnetic field increases. That's it. This coefficient, mu, is just a fixed constant. It's similar to epsilon naught, but only for magnetic field. Magnetic field is very weak because you see this constant is small. K is 9 times 10 to the 9th. Yeah. Electromagnetic field has two components, electric and magnetic. And magnetic component usually is much, much weaker, generates much weaker force. So very often we just neglect the presence of magnetic field. Now, let's calculate it. Electric current is out. Magnetic field vector points like this, as we know. That's the magnetic field line. So magnetic field strength equals 4 pi times 10 to the negative 7 times 5 amps divided by 2 pi times 100 centimeters in 1 meter. So pi over pi, 4 over 2, 2 times 5, 10, 10 to the negative 6. And as we know, the standard unit for magnetic field strength is Tesla. The question is, what do we do if we have several sources of magnetic field? The answer is the same, which worked for forces, which worked for electric field. We have to add them as vectors. That's a superposition principle. Right here, right now, we have two wires. Each individual wire generates its own individual magnetic field. So we have to calculate first, we have to calculate second, we have to add them up as vectors. And to do that, first we need to see those vectors. First wire, thumb, fingers. Right here, magnetic field of the first wire points away from us into the screen. Let's call it B1. Second wire, current. So has to be inside. The wire has to be inside the fingers. So magnetic field lines are circular like this. Like this means right here, magnetic field vector should point out of the screen at us. Technically, they're supposed to be located at exactly the same point, but in that case, it would be hard to see. So that's why I spaced them a little bit. So now, we have an agreement. Everything which points to the right is positive, normally. Everything which points up is positive. And a part of that agreement is z-axis. Also points at us. So everything which points toward us is positive, and everything which points away from us is negative. So we can say that B1 has a negative component, negative 1 times magnitude of B1. And B2 has a positive component, positive 1 plus 1 times magnitude. So how do we calculate Z? How do we calculate the net field? B Z net equals B Z1 plus BZ2, which means magnitude Now all we have to do is just constant first current, first distance, same constant, second current, second distance. 4 pi 10 to the negative 7. Okay, that's what we know. We actually don't need the whole thing is given to us. Constant times current number 1 over 2 pi. This whole combination is given to us just to speed up the calculation. It equals to 10 to the negative 5th. And 10 to the negative 5th, and we need to calculate by the distance from the first wire to the location where we measure or calculate it. R1 equals 30 centimeters from each wire. We cannot use centimeters. Have to convert into meters. Negative 5.3 plus current number 1 is twice higher than current number 2, which means current number 2 is a half of the current number 1, which means this whole combination should be equal to a half of the given number. 1/2 negative 5, same distance. That's minus 1. Yeah. 1/2 minus 1. That's actually negative number. Negative half negative 5.3. Negative 10 to negative 5 divided by 0.6, wherever it is, Tesla. What does negative sign mean? It means magnetic field has a component negative relative to positive z direction chosen at us. So it means net field points away from us. What is the strength of that net field? Well, this number, magnitude of that number. 10 to the negative 4 divided by 6, 10 over 6 kilotesla. 5 over 3, 1.6 kilotesla. Any questions? That's the last slide for today, because technically right now, every problem about force acting on a wire, force acting on a charge, an electric field generated by 1, 2, or many wires can be done. All right, thank you very much. So I'm going to have my office hours after I move out from this room. Please don't forget to pick up your exam. Yes, if it's a quick question.
How to use the equation? I'm sorry, you have to ask.
Okay.
So, for this one, I'm not quite sure what I got points off on, but for this, I
1, 2, 3, 4, 1, 2, 3, 4, 72 minus 6 is just not 78.
Yeah, but
It's
I changed
76. You just 72 minus.
I just changed it. It should be a plus. I was thinking about it last minute. I changed it.
But it shouldn't be a plus. It should be negative number.
Yeah, minus negative 60,000.
No.